All right, so we're starting Unit 8, which is a wonderful unit. Great topic about estimating using confidence intervals. And when we're done with Unit 8, you're going to be rock stars at this. But this is new and different, got some different terminology in it. So today we're not really finding a confidence interval. We're just talking about what a confidence interval is, getting some of the notation and the vocabulary down because this is such a different concept using things that you already know. So this, the notes are 2 pages front and back like this, should be really short, but I'm going to go slow so that your brain has a chance to process everything. So make sure that you are where you can focus and concentrate and process. Again, this is not a long video. 8.2 is a long video, but it's not as upper level thinking as this one is because we're laying the foundation, okay? So we're talking about confidence intervals. Before we start, I want to compare what we're going to do to throwing darts on a dartboard. Okay, so let's say we have a dartboard and I stand across the room at a bar and I throw a dart to a dartboard, and this is a pretty good average size of a dartboard. How confident am I, now if I do this on a regular basis, how confident am I that I'm going to hit the dartboard? Well, you know, pretty confident if I do this a lot. But if I take my sweet husband with me and he hardly ever throws darts, he's going to hit the wall all around the edge. So he's not going to be as confident that his dart is going to hit the dartboard. However, if we switch dartboards and get a really big dartboard, now, do you think that Mr. Patterson is going to be just a little bit more confident that he can hit the dartboard? Because it's bigger, okay? So the bigger the dartboard, the more confident you are that you're going to hit it. The smaller the dartboard, the less confident you are that you're going to hit it, okay? So just keep that in mind. Here we go. Assume that a population distribution is normal with a standard deviation of 20. We take a simple random sample of size 16, and the sample mean is X bar, because this is a sample, 240.8. So I have the standard deviation of the mothership. I take a sample of size 16, and I have the mean of my sample. Okay? Standard deviation of the population, I have the mean of the sample, and size 16. The question says, what is the mean of the population? What is the mean of the mothership? Now, we have said that if you know the mean of the mothership, then you can assume that it's an unbiased estimator and find the mean of the sampling distribution. I take a bunch of samples, they're all going to have different means, but when I average all those means together, I should get the population mean. Okay, well, this is going backwards. This is saying, okay, I know the mean of the sample. What is the mean of the population? If I take a sample of students at South Stokes and find their GPA, should that be exactly what the average GPA is for every single student at South Stokes High School? No, absolutely not. Should be close. If we take a good sample, it should be close. We take a good, fair sample. Should be close, but not necessarily going to be the same. A point estimator is a statistic. Statistic is of the sample. So we're talking about X bar and p hat. A point estimator is a statistic that provides an estimate of a population parameter. So guys, we're going to be using those two things to estimate the big guns, mu and p. The value of that statistic from a sample is called a point estimate. So x bar and p hat are point estimates. If x bar is 240.8, that is our point estimate for the population mean. Does that mean that the population mean is 240.8? No, absolutely not. Should be in the ballpark, but no. I just took one sample. So that mean, again, if I took a good sample, this was only of size 16, so it's not a great sample, but if I took a good sample, then that's a good estimator of the population mean. But it is not going to mean that the population mean is 240. So that's a big no. But it's probably going to be around that number. So now the question is, okay, how close? How close is the population mean to 240.8? So guys, here's what you got. You got X bar. We're going to call X bar the bullseye of our dartboard. Here's our dartboard. What I want is I want to know how big does this dartboard need to be for you to be, I don't know, 95% confident that mu is in the dartboard, that the dartboard captures mu. So we're going that big to the right and that big to the left, that mu is somewhere in here. Now, if I make a smaller dartboard, and there's X bar, I'm not going to be 95% confident. I'm less confident, smaller dartboard. Smaller interval for X bar for this dartboard to capture the actual mu. So maybe, I don't know, I'm 75% confident. If this dartboard were even bigger than this, then maybe I could be 99% confident that the dartboard captures the actual mu. Okay. X bar is the guy we know. He sits in the middle of our dartboard. Now what we're going to decide is, okay, how far to the right and how far to the left, how much wiggle room do you want to add and subtract to that X bar to give me an interval where you can be 95% confident that that interval captures the actual mu. The sampling distribution of X bar describes how the values of X bar vary in repeated samples. That part's important. I'm going to say that one more time. The repeated part is really important. The sampling distribution, so sampling distribution, many, many, many samples of X bar describes how the values of X bar vary in repeated samples. Can we find the mean and the standard deviation of the sampling distribution? Well, the mean of X bar is mu. Well, I don't know what mu is. I know it at one X bar. I know what one sample's X bar is. That's it. I know him. What was he? 240.8. But I don't know mu. So I can't find the mean of the sampling distribution. Can I find sigma sub X bar? Well, absolutely. After you go past the 10% condition. So let's say we do that. Okay. Now I can find this. So that was sigma over the square root of n. Well, they told me sigma. They told me sigma of the mothership was 20. And they told me my sample size was 16. Square root of 16 is 4. 20 divided by 4 is 5. So guys, I know the standard deviation of the sampling distribution. I cannot find the mean of the sampling distribution. Because remember, mu is an unbiased estimator. Well, I don't know what mu is. Okay. Remember the 68, 95, 99, 7 rule? It seems like 5 years ago that we did that. 68, 95, 99, 7 rule. Back when y'all were just young little budding statisticians on your journey. Now you're old and seasoned and a little rough around the edges. Okay, so the 68, 95, 99, 7 rule. So remember, 68% of your data lives within 1 standard deviation. 95% of your data lives within 2. So there's 68% of my data. There's 95% of my data. And there's 99.7% of my data. Okay, now I want you to think about this as the width of a dartboard. So if my dartboard goes 1 standard deviation on either side of mu, remember you don't know mu, so in its place we're going to put x bar. So if I take x bar and I add and subtract 1 standard deviation, then I can be 68% confident that that dartboard is going to capture the elusive mu that I don't know what he is, and I'm never gonna know what he is. I'm just interested in an interval that he lives in. So that's what I'm going to do. I'm going to take my x bar, which was 240.8, and I'm going to add to it, let's see, what was my standard deviation? 5 from just up a little bit. So plus or minus 5. So that would be 235.8 if I subtract 5, and then all the way to 245.8. So we're going to write this as an interval. So 235.8, comma, 245.8. Now this is not a point. This is a from here to here. It's like, and I don't know if y'all have done this in Math 2 or Math 3 yet. There it is. It's another way to write an interval with the parentheses. Okay, so that's the width of my dartboard. My dartboard is 10 units wide because I went 5 in each direction. So I am 68% confident that the interval from 235.8 to 245.8 captures the true proportion, or the true mean of all whatever it is that we're measuring. I don't even know what we're measuring. Now, you want to get more confident, you want to get a higher percentage, you got to up your dartboard. So if I want to be 95% confident, okay, well now you got to go 2 standard deviations. So now I'm going to do x bar plus or minus 2 standard deviations, and this is going to get me 95% confidence. So higher confidence, but it's going to be a bigger interval, a bigger span for mu to live in, because I'm going to be more confident that I'm going to hit the dartboard. So that would be 240.8 plus or minus 2 times the standard deviation of the sampling distribution. So now I'm going to add and subtract 10. So that's going to be 230.8 to 250.8. Now that gets me 95% confident that mu lives in that interval. Higher confidence, bigger interval. You want to go 99.7% confident? That's fine. We're going to go 3 standard deviations on either side of my point estimate, which is my x bar. I am trying to pin down mothership information that I don't know based on one sample. It's a very presumptuous thing to think that you can tell me what the mothership information is based on your sad little sample of 16 people. And that's why you're not giving me an exact value. Like, you don't know what mu is. You're not going to know what mu is, but you're giving me a range that you are 95% confident that mu lives in this window on this dartboard. I'm 95% confident that the mothership mu is in between a 230.8 and a 250.8. 95% confident. That's pretty good. Pretty good. You want me to be more confident? Well, then I'll give you a bigger interval. You want a smaller interval? You're going to try to pin it down a little bit more? Okay, well, now I'm going to back off my confidence level a little bit. All right, whenever x bar is within 10 points of mu, then mu is within 10 points of x bar. Well, okay, duh. This happens in about 95% of all possible samples. So the interval from x bar minus 10 to x bar plus 10, that's what we're doing. We've already done that. Because of course I got excited and jumped ahead. That's what we're doing right there. When we plus or minus 10, that's what this is talking about. So the interval from x bar minus 10 to x bar plus 10, that's the 230.8 to the 250.8, captures the population mean, mu, in about 95% of all samples of the same size. So then we do this, 95%, 240 plus or minus 2 times 5. We've already done all that up yonder. So I'm 95% confident. And this is my dartboard. That's the width of my dartboard. The big idea is that the sampling distribution of x bar tells us how close to mu the sample mean x bar is likely to be. Statistical estimation, which is what you're doing, you're estimating, just turns that info around to say how close to x bar the unknown population mean mu is likely to be. A C% confidence interval, so 95%, 68%, 99.7%, whatever, confidence interval gives an interval of plausible values for a parameter. Parameter is mothership information, so either mu or p. The interval is calculated from data and has the form, okay, here we go, point estimate, that is either x bar or p hat, because those are both point estimates depending on whether you're dealing with means or proportions, plus or minus the margin of error. And that's your wiggle room. That's how much you're adding or subtracting, or adding and subtracting to your point estimate. Now we'll focus big time on how to find the margin of error exactly in the next 2 lessons. Right now you're just understanding the concept of I'm taking this x bar and I'm adding a value to it and I'm subtracting a value from it to get this window, to get this dartboard, to get this interval. Let's see. Yeah, interval right there. The difference between the point estimate and the true parameter value will be less than the margin of error in C% of all samples. The confidence level C gives the overall success rate of the method for calculating the confidence interval. That is, in C% of all possible samples, the method would yield an interval that captures the true parameter value. I know that sounds like gibberish. It's okay. It will sink in. Just stay with me. All right. Here's a follow-up question that has a, you have to choose larger or smaller. Okay, so let's see if we can do this. The larger the confidence interval, okay, so guys, picture a dartboard. The larger the dartboard, so the bigger the dartboard, nope, back that up. The larger the confidence interval, the larger the confidence interval, so 95, 99.7, 68, the larger your confidence level, the larger or smaller of the interval. Well, think about Mr. Patterson playing darts. If we are super confident that he's going to hit that dartboard, tell me about that dartboard. It's going to be big. It's going to be big. So as your confidence interval goes up, your interval is going to go up. The size of your dartboard is going to go up as your percentage that you're confident. But if you were to say, you know what, I'm 68% confident I got it. Here's an interval. I'm 68% confident that the parameter lives in that interval. Well, that's not super confident. So that's not going to be a super big interval. So if you want a smaller interval, if you're trying to say, haha, I think I got it. I've got it narrowed down to this tiny interval. Okay, well, it's a tiny interval. That means I'm not super confident that I have it. So I have to back off my confidence level, my percentage. But if I say, ooh, I am 99.7% confident that I have captured it, well, that's probably a really big interval. So it's kind of a trade-off. Do you want to be really confident, yet have this huge interval that really doesn't narrow it down that much? Or do you want to have this tiny interval that really narrows it down, but be less confident that you got it? We are C% confident, 68, 95, 99.7, that the interval from blank to blank, small end to the large end, captures the true proportion of all red cars in the parking lot. Captures the true mean GPA of all students in Stokes County. So captures the parameter in the context of the problem. The true length of all bass fish in Lake Norman. All right. Who will win the election? 2 weeks before a presidential election, a polling organization asks a random sample of registered voters the following question. If the presidential election were held today, would you vote for candidate A or candidate B? Based on this poll, the 95% confidence interval for the population proportion who favor candidate A is 48% to 54%. So they took some samples, they got some information, and they found, like, this is the result. This is their confidence interval from 48% to 54%. I'm 95% confident that the mothership population proportion P herself, not P hat, P, just plain P, is in this interval from 48% to 54% of all registered voters based on this sample of registered voters. But this is of all registered voters, is in that interval right there. Interpret the confidence interval. All right, here's your sentence. Listen to it first, and then I'll say it several times and let you write it down. But just listen to it first. We are 95% confident that the interval from 0.48 to 0.54 captures the true proportion of all registered voters who favor candidate A in the election. There are some very key words there. So let's write. We are 95% confident. So first you're stating what is your confidence level? How confident are you? I'm 95% confident that the interval from 0.48 to 0.54. And if you wanted to go 48% to 54%, that would be fine. All right, the interval from here to here captures the true, important word, the true proportion of all, another important word, registered voters. Who do what? Who favor candidate A in this election. We are 95% confident that the interval from 48% to 54% captures the true proportion, the pure proportion, the mothership proportion, the true proportion of, and then to emphasize the fact that this is a population, dude, we're talking about here, we're going to use the word all, of all registered voters, not our sample, not our sweet little random sample, no, of all registered voters who favor candidate A in this election. I took a sample, I gathered some data. Based on that data, I can be 95% confident that the interval from 48% to 54% captures the true proportion of all registered voters who favor candidate A in this election. I don't know what P is. I don't have a clue. I'm never going to find it. But I'm 95% confident that it's in between 48% and 54%. 95% confident that it lives in that interval right there on that dartboard. From 48% to 54%. I'm 95% confident that it is in that interval. Okay, now, you did not build that interval. That interval was given to you. Now, for 8.2 and 8.3, you're going to be building that interval. But right now, it's sitting right there on a silver platter. So here's part B. What was the point estimate? What was the margin of error? Well, that interval is centered on the point estimate. The point estimate, now the point estimate is your statistic. So that is either X bar or P hat. In this case, it's a P hat because we're talking about proportions. So the point estimate is your P hat. So it is the point estimate plus or minus the margin of error. That's what gives you those two numbers. So your point estimate is sitting smack dab in the middle of it. So how do you find what that is? Add them up and divide by 2. Find the middle. Add them up and divide by 2 and find the middle. And it turns out to be a 0.51. So P hat is a 0.51. That is what that confidence interval was started from. That's where it started. I took that P hat of 0.51 and I added something to it and I subtracted something from it, and that's where I got my interval from. Speaking of adding something to it, subtracting something from it, what did you add and subtract from a 0.51 to get a 0.54 and a 0.48? That is your margin of error. Well, if this is a 0.51 and I got to a 0.54, that's 0.03. And if this is a 0.51 and that's a 0.48, that's a minus a 0.03. So my margin of error is a 0.03. I didn't use any formulas for that. Just find the middle and then figure out what was added or subtracted from the middle to get to those two endpoints. Okay, based on this poll, a political reporter claims that the majority of registered voters favor candidate A. Use your confidence interval to evaluate this claim. I think this guy's claim is crap. I am 95% confident that the interval from 48% to 54% captures the true proportion. He's saying that the majority means greater than 50%. Well, my interval contains values that are less than 50%. I mean, yes, it contains values that are over 50% as well. And the true proportion is only one of those values. It is only one value from 0.48 to 0.54. And I'm 95% confident that it's in there. But 0.48, 0.49, and 0.50 are all not majorities. So I think this reporter, it has an unfounded claim. It could be true, but based on this, I'm 95% confident that it's in between a 0.48 and a 0.54. Well, some of those values are less than 50% or less than 51%, which would be the majority. So I think that this does not give convincing evidence to support this claim, or that this gives convincing evidence to say that this reporter's claim is bad. Any value from 0.48 to 0.54 is a plausible value for P. And because there are values in our interval that are less than 51%, the interval does not give convincing evidence to support this reporter's claim. Okay, this guy's important. We're going to refer to him several times. I'm going to say, remember that graph with the green lines and the red dots? This is what I'm talking about. All right. We have a sampling distribution of X bar. Okay. A sampling distribution means that I have a crap ton of samples. Okay. So here I go. Each red dot is a mean of a sample. Each red dot is a mean of a sample. So let's see. I've got, if you count all the red dots, I've got 25 samples. Oh, here it is. 25 samples. Okay. And all of these little red dots, including that red dot on that blue line, including him, if I took X bar and added and subtracted, and here's the mean, and I added and subtracted 2 standard deviations. Okay, so here's 1, 2, and here's 1, 2. So here's what I'm going to do. I'm going to draw a terrible straight line. All right, so see all those red dots that are in between 2 standard deviations? I'm 95% confident that mu will be in between those 2 black lines. Well, how many X bars did I miss? I missed 1. One of them is outside my interval. So that means it captured 24 out of 25 of them. That's 96%. Well, that's almost right in line with being 95% confident. So when I do this over and over and over again in repeated samples, I can be confident that I'm going to capture the true proportion, the true parameter 95% of the time. And on this case, it was actually 96. Okay. So that is a confidence level. There's a difference between a confidence interval and a confidence level. Okay, almost done, guys. Stay with me. A confidence level. To say that we are 95% confident is shorthand for saying in repeated samples of the same size from this population. Approximately 95 of the resulting confidence intervals will capture the true parameter value. And that is a rubber stamp sentence that you have to memorize. In repeated samples of the same size, so you have to do it a bunch and they have to all be uniform. They have to all be the same size. Otherwise, you're going to get a different standard deviation. So your N has to be the same. So in repeated samples, so do it a bunch of the same size, same N from this population, approximately 95% of the resulting confidence intervals of everything you get from all of those samples will capture the true parameter value. Think about the black lines I drew. I only missed one red dot. And that's why you have that word approximately in here. We did 2 standard deviations, so I'm going to capture approximately 95% of them. And I did. I actually captured 96% of them. Approximately 95% of the resulting confidence intervals will capture the true parameter value. The confidence level does not tell us the chance that a particular confidence interval captures the population parameter. Okay, now these 2 sentences are good because they talk about the difference between an interval and a level. The confidence interval gives a set of plausible values for the parameter. That's what we found when we were doing x plus or minus 2 theta, and we got, I don't know what it was, 48% to 54%. That's a confidence interval. It gives us a set of plausible values for mu or p. The confidence level describes the long run, repeated samples, capture rate of the method. All right, here we go. So I'm going to give you an example, and then we're going to write, or not going to write, we're going to read a sentence for the confidence level and the confidence interval. The Pew Internet American Life Project asked a random sample of 2,253 U.S. adults, do you use Twitter or another service to share updates about yourself or to see updates about others? Of the sample, 19% said yes. Of the sample, this is a sample. This is sample information. This is P hat. According to Pew, the resulting 95% confidence interval is 0.167 to 0.213. So my sample, my P hat, is 19%. We are 95% confident that P lives in between a 16.7% to a 21.3%. P is somewhere in there. I am 95% confident that P is in there somewhere. I don't know what P is, never gonna know what P is. But based on that sample, I'm 95% confident that P lives in between those 2 percentages. Okay, so now we're going to interpret the confidence interval and the confidence level. I'm going to read each one twice and with intention. Here you go. Confidence interval. We are 95% confident that the interval from 0.167 to 0.213 captures the true proportion P of all U.S. adults who use Twitter or another service for updates. I'm emphasizing words that are an absolute have to. Otherwise, you're going to write so many of these, they're going to be exactly this. Like you're going to start writing the exact same sentence I'm writing. We are going to be exact because you're going to do so many of these. All right, here I go. I'm going to go again. Confidence interval. So I am interpreting the interval. We are 95% confident that the interval from 0.167 to 0.213 captures the true proportion of all U.S. adults who use Twitter or another service for updates. Put it in context of the problem. Confidence level. Have to do it a bunch, have to do the same size. In repeated sampling of 2,253 U.S. adults, approximately 95% of the resulting confidence intervals would capture the true proportion P of all U.S. adults who use Twitter or another service for updates. I'm going to do this a bunch. I'm going to get a bunch of intervals. This is the percentage of those intervals that will be successful in capturing the true proportion. In repeated sampling, have to do it a bunch, of 2,253 U.S. adults, same size, approximately, because I could be off a little bit, 95% of the resulting confidence intervals, all those intervals that I'm going to get after doing all those samples, of the resulting confidence intervals will capture the true proportion of all U.S. adults who use Twitter or another service for updates. When you're doing your homework, use these two sentences to help make your rubber stamp of these interpretations. Rubber stamp, like you just, it's the same every time. You just change the numbers and a little bit of the interpretation. All right, calculating a confidence interval. You don't always have to do a 95% confidence interval. We just did because it's 2 standard deviations. It's just a nice round number. But here's how you're going to do it in 8.2 and 8.3. You're going to take your statistic, which is either p hat or x bar, and you're going to plus or minus, so you one way and then the other way. We're going to find a critical value, you don't need to know what that is yet, it's okay, times the standard deviation of your statistic, which you know how to find the standard deviation of p hat, and you know how to find the standard deviation of x bar. A little square root of pq over n, and little sigma over the square root n. And that is that critical value times the standard deviation. That is your margin of error. That both those things multiplied together, that is your margin of error in blue. We would like a high confidence. Our method almost always gives us correct answers and a small margin of error. That means we pin down the parameter quite precisely. However, that's very hard to do. I want to be super confident and I want a tiny dartboard. Well, you can't have both. If you want to be super confident, you need a big dartboard. If you want a little dartboard, then you got to lower your confidence. The margin of error gets smaller, meaning your dartboard gets smaller. Your plus and your minus gets smaller when the confidence level decreases, or when your sample size increases, because that makes your standard deviation get smaller. A smaller interval causes us to be less confident that it will capture the true our parameter. So 80% smaller percentage, smaller dartboard. 95% higher percentage, bigger dartboard.